Okay, so the title of the talk is Jupiter Rediscovered, and I'll be talking about this image here in a little bit, but it's an image that was taken by the Juno satellite, and but I actually put it together. So what we're going to do is we're going to give a little overview of Jupiter and what the Juno mission is, and that's the rediscovery associated because we now have a real scientific mission going on that is delving more deeply into the what's going on in Jupiter than ever before. We'll talk about the internal structure, the belts and zones, the bands that you see on pictures. We'll talk about the gravitational field, the polar regions, and then the magnetosphere. A little bit of just overview of Jupiter. Jupiter is about 11 times the size of the Earth. You can see in this diagram, there's Earth. Jupiter is one of the gas giants. It is so massive that it actually is 2.5 times the mass of all the other planets in the solar system. It rotates extremely fast. It actually has the shortest day of any of the planets. It only has a 10-hour day. And it's not a solid body, it's a gas giant, and so it rotates a little different. The polar region takes 5 minutes longer to go around than the equatorial region. A little more information about Jupiter. Its distance to the sun is 5 times further away than the Earth is, so it makes it about 490 million miles away. It has a 12-year orbital period around the sun. Interesting, it's at a resonance with Saturn. So for every 5 Jupiter times around the sun, Saturn goes around twice. Jupiter has almost no axial tilt. The Earth has about 23.6 degrees. Well, the axial tilt at Jupiter is about 3 degrees. So we always see it equator on. The temperature of the outer clouds is a nice toasty minus 234 degrees Fahrenheit, but the core temperature is a little warmer at around 43,000 degrees Fahrenheit. Now a little bit about Juno. Juno is a satellite, a spacecraft that's currently orbiting around Jupiter. I'll talk a little bit about its orbit, but it was first launched in 2011, and it made a pass around the inner solar system and made a flyby on Earth 2013 and did an insertion in Jupiter in 2016. The actual satellite is shown here. It's the solar panels are about 30 feet in length. The center part is about 11.5 feet. If we look at the next picture here, this talks a little about the Juno, the instruments on Juno. So it has the capability of measuring the gravity of Jupiter. I'll describe how that's done. Its magnetic field. It has a microwave radiometer, so it can probe deep into the planet, as much as 300 kilometers. It has the ability to measure magnetic fields and plasma particles. It has both a UV and an ultraviolet camera. And not to least, although it's quite small, it has something called the Juno Cam. And the Juno Cam takes regular color pictures. It's not a very high resolution camera. It's only 2 megapixels. And it's complicated because the satellite is actually rotating while it's taking pictures. So it's a special camera. Even though it's not real high resolution, your cell phone has, probably 10 times the resolution of the Juno Cam. But it has one advantage: it's a lot closer to Jupiter than we are, or the Hubble or whatever. The orbits around Jupiter are very interesting. They're 53-day orbits. They were only supposed to be 14-day orbits, but they ended up as 53, and they decided to leave it that way to avoid screwing things up. It's going to make 33 of these orbits, and eventually it will cover the entire planet. You can see in this diagram all the various orbits it's going to pass. And the orbits are extremely unusual. It's totally different from anything before because it goes over the poles. And so I'm going to show you a little video here of actually one of the passes over the poles that the Juno satellite is making. And it's Beethoven's Moonlight Sonata playing. This is the North Pole. It gets really close to the planet at the equator within 2,500 miles. Then it zooms out over the poles to about 60,000 miles. And we're going to come up to the South Pole here shortly. This is a picture, and as I mentioned, the orbit is quite unusual. It's going over the poles. So we're getting the first time ever view of the poles. This is a view of the South Pole. It's a picture that I did not take. Juno took it, but I assembled it. It's assembled of three different orbits, three different times, because the camera does not ever get the entire planet in its view at any one time. And it was quite tricky because it's not just three different pictures taken at the same time. They're on pictures taken at different times of the orbit. So, but I managed to put it together, and this is what it is. You're looking at, we'll talk some more about this, but you're looking at the cyclones. So it looks totally different from the poles than it does from when you look at an equator view. And these cyclones are about 6,000 miles in diameter. The mission of Juno is to measure the composition of the planet, its gravity field, and its magnetic field. It's also a goal is to determine, if we can, what the overall, whether it has a rocky core. And another big question is, how far down do these surface winds go? They are very high. They get up to almost 400 miles an hour. So one question is, how far down do they go? We'll get into that. So this is just a more detailed view, or without the rest of the words of the South Pole. So a little bit about the atmosphere. This diagram was essentially made during the Galileo era, which was in the mid-90s, and it shows the upper part of the atmosphere of Jupiter. This is nominally considered the surface, which is 1 bar. So there is no real surface on Jupiter, but you can see it consists of ammonia, ammonium hydrosulfide, water, and then it transitions into hydrogen and helium. The bulk of the planet is hydrogen and helium. In fact, Jupiter may be a failed star that didn't ever quite make it hot enough to start a nuclear reaction. This is now a view, a cross section of the entire planet, starting with the atmosphere at the top. Next is a layer of a weakly conducting layer that has some particles, some junk in it, silicate molecules that came from various places, asteroids and other things that Jupiter has collected over its lifetime. Then it transitions, you can see the scale here, this is 10,000 miles. Then it transitions into a highly conductive layer of highly conductive hydrogen. Hydrogen molecules, but still exchanging enough electrons between the molecules that is conductive. And this is where we think the magnetic field is created, and I'll talk some more about that. Then there's some helium rain clouds. Helium is condensing, and then the bulk of the planet is this metallic, bulk of the planet is this metallic mantle, which is totally, it's a superfluid, or it's liquid hydrogen, and it's ionized. So it's protons and electrons floating around. And then down at the very core is the denser materials, iron, but it's not thought to be solid, even right down to the core. And here you can see what the Earth's radius is. It's quite small. So getting into some of the data from the Juno satellite itself, this is a diagram that was made with the microwave device. It's a radiometer, and it was able to measure these various cloud layers that where I mentioned earlier. And you can see what the temperature does. It starts out It starts out quite cold and then warms up as it gets down to the 200 kilometer region below. One of the big questions, one of the big surprises, however, which was totally unknown before the Juno mission, is that there's the layers underneath. It was once thought that there was an ammonia layer, but it was sort of uniform. But what we now find out is that ammonia layer is not uniform. And in fact, it has an area around the equator where it upwells and to the upper part of the atmosphere. And this next diagram shows that in some more detail. Here we see the ammonia layer down and then, but it shoots up and then it is probably the source of the upper ammonia atmosphere on the at the cloud upper cloud layer. And this ammonia layer is thought to be an analog to what's going on Earth, where in Earth you have a water vapor at our equator coming up and spewing out over the lower latitudes. Well, ammonia is essentially doing that on Jupiter. So now turning a little bit more to the more traditional views of the planet. Again, I'll talk a little bit more about this picture, but this is a picture that was taken about 40 degrees southern latitude. And so here you have the southern part of the planet, but you can see the traditional, what are called belts and zones. So the white areas, the light areas are called zones, and they are made up mostly of ammonia, and it's an upwelling of material from the inside down below to the surface. The dark areas are made out of denser materials, and they're more downwelling, and they move in opposite directions. The zones are moving eastward, whereas the belts are moving westward, and there's some very high winds in between them. And you can also see other features of the planet, which are various huge complicated storm patterns, as well as cyclones. And here you have the giant red spot, which we'll talk some more about. Yeah, and this just shows the picture of the planet alone. This was a very difficult picture to assemble, I can tell you. It's 4 different images, but this was all taken on the same orbit. That it was on the 20th orbit around the planet. And what was difficult about it is that the camera, when it's at the equator, is within 2,500 miles. But when it gets over to the poles, is 60,000 miles away. So each of the pictures is taken at a different distance from the planet. So to assemble this into something that actually looks right was quite difficult, because the pictures are all at different distances. So they all had to be scaled so they would fit together. And I've seen other versions of this, and I happen to like my own as well as I've seen anyone else's. So, yeah, so this picture was taken from a range of about 11,000 miles to 42,000 miles, all 4 of them went separately. Here's a picture that is actually a video, which I'll play for you here in a second. It was taken originally, it's actually assembled of 32 pictures that were taken by the Voyager 1 satellite in 1979. And it has this nice feature that you can actually see what's going on in the planet. So isn't that cool? You can see the zones going this way and the belts going the other way. I interrupted it. You can see the giant red spot. See how it's turning counterclockwise. I think it's so cool. All right. Okay, so this is now a diagram of the winds that have been measured by the Juno satellite. These are the actual wind velocities, and you can see the peak velocities occur both in the southern and the northern hemisphere. But the highest velocities are in the northern hemisphere, and they occur between this zone and the adjacent belt. And then this is just a graph of the anomaly, the wind speed beyond the average wind speed. And you can see there's 2 big spikes to it. Now this is it looks similar, but what it is actually a measure of the gravity field on Jupiter. And the gravity field is definitely not uniform. And it has all of these interesting zigs and zags to it. And this is, again, the anomalous field. This is the average here, and these are the different deviations from average. And you can see there's some rather large deviations, both in the northern and the southern hemisphere. And these deviations pretty much correspond to the same places where the wind speeds are the highest. And it would be interesting, and let me just mention how the measurement of this field was done. There's a transponder on the satellite in both the X and the K band, and it's transponding back to the Earth. And so what's actually going on is that we're measuring the Doppler shift of the actual motion of the satellite as it's going around the planet. And it's that Doppler shift, they're translating that into variation into the gravity fields. And so this just shows a comparison between the wind speed diagram and the gravity speed. And it's not a perfect correlation, but there's anomalous, the big dips in the north and the south pretty much correspond to where the wind speed changes, the gravity field changes at about, so they're definitely correlated. And now talking a little bit more about the details of what's going on. So there's Jupiter, as I mentioned earlier, Jupiter has no surface. So these convection patterns that we saw earlier, we don't know how deep, they didn't know how deep they went. They thought they might go down maybe 300 kilometers, but that's been one of the major puzzles that we've been, that they've been trying to sort out with this mission. And so by measuring that gravity asymmetry, or the variation in gravity along the, as a function of latitude, they've been able to do some modeling. And the modeling results are shown here. So this is just the scale of the wind speed on this side. Just one is the high at the surface. This is at the equator. So this is the wind speed at the equator as a function of depth. And as you can see, it's still quite high. We're talking about maybe 400 miles an hour up here, and it's still quite high. And it continues down below 3,000 kilometers. This was a big surprise that it was that these things were that deep. This diagram is the inflection point, like right here at the inflection point, as a function of the latitude. So here it is, and so this is the depth as a function of the latitude. So that inflection point is about a little over 2,000 kilometers below the surface at the equator, and gradually gets less and less, so that the depth of these bands and belts, zones and belts, goes to zero at the poles. So this is another diagram that NASA has produced, which just sort of dramatizes, it's a little bit of a cartoon that dramatizes what's going on underneath the surface of the planet. So that's the core rotating under, pretty much fixed. But here you see the zones, the belts and the zones moving in opposite directions. But it shows, it gives us some indication that it's down to 3,000 kilometers. And then below that, the planet is essentially this liquid, highly conductive hydrogen liquid that is rotating as essentially almost as a solid body. Now, one of the interesting things is, with it going down 3,000 kilometers, it's been estimated that these streams, that this atmosphere constitutes 1% of Jupiter's mass, that essentially the moving atmosphere, if you want to call it that, is 1% of the mass, whereas in comparison, Earth's atmosphere is only 1/1,000,000th of the total mass of the Earth. So, okay, so now even going into a little more detail of what's going on, in addition to these belts and and zones, there's all these amazing storms that are on the surface of Jupiter. And this is a picture that was a composite of 3 images on the 20th orbit that I put together. And you can see some of these incredible patterns. And this next picture is one that looks more like a Van Gogh painting. If any of you have seen the exhibit, my exhibit in the library, this is there. But it just shows some of these incredible storms that occur on the surface of the planet. Now, this one is I look at it carefully and I said, well, it looks like there's a character here. There's got two eyes and a head and some strange looking arms, and then these long legs, and then here we have this snake over here. And so we're going to transition from this into this picture. Now, this is actually on the same part. This was 2 of the 4 pictures that I made to show that whole southern hemisphere image. These are the upper 2, and so you can see in some great detail of the great red spot here. And the next picture is even more detail. This is a different orbit, but it just, you can see how much detail there's never been this level of detail in any of the previous images, even from Hubble of Jupiter. Now, the interesting thing about this, the Great Red Spot, is it rotates at about 250 miles an hour, and it makes a single rotation in about 6 Earth days, or about 14 Jupiter days. Its dimensions are about 10,000 miles this way and about 8 this way. So it's a little bigger than the size of the Earth, maybe 1.3 times. The color is thought, even though most of these anticyclones are white, this one storm is so strong, it's thinking that it's bringing up some of the elements from the ammonia hydrosulfide down below up to the surface. In fact, but this pattern, the actual spot is smaller than it used to be. About 100 years ago, it could have held about 3 of the Earths in it. And it's thinking that it might actually disappear in the next 20 years. So we're going to turn now to the polar regions. And I've shown you this picture already of the South Pole. And so this is, it's people have analyzed how is it that the bands and belts that we're familiar with transition into this. And there's been some solid modeling that's done of this. And people have sort of come up with some theories as to why this is happening. But these patterns are amazingly stable. They don't change, unlike the storms in the that are occurring in the bulk of the planet. The storms up here, these cyclones, which are about these center section of cyclones, each of these are about 4,000 to 6,000 kilometers or miles in diameter. Now, this is an IR image of the North Pole, and there are 8 of these cyclones around the North Pole surrounding a central cyclone. And then this next picture shows, it's sort of the same image for the North Pole, but now it shows the South Pole, and there are 5 cyclones surrounding the center. But what's amazing is over a period of 7 months, many orbits that the satellite has made, these patterns haven't changed. And there's kind of a mystery as to why they continue to look alike. That's the only reason I could have done that image of the South Pole that took 3 orbits, because the images didn't really change very much in between those 3 orbits. These pictures over here are true color, color pictures. They're, whereas this is infrared, this is visible light pictures of the same areas. Actually, you can see a lot more of that. These various cyclone patterns are much more visible in the IR image. And another feature of the polar region is lightning. And this has been first seen by Voyager 1, and it's seen, Hubble has photographed some of the lightning as well. But during the first 8 now, but Juno goes over the poles, and so it's gotten a great view of it, and it's seen something like almost 400 lightning discharges in the first 8 flybys. And what's unusual about the lightning on Jupiter is that it's at the poles. Now, in the Earth, lightning tends to occur in the temperate latitude. It's not up in the poles. But Jupiter gets about 25 times less sunlight than the Earth. And so the thinking actually is that that sunlight stabilizes the atmosphere in the lower latitudes. But most of the heat that comes up to that's generated in Jupiter comes from inside. And and as a result, and the sunlight isn't reaching the poles at all almost, that this lightning all occurs in the polar regions. Now we're going to talk about the magnetic field. Jupiter has a extremely high magnetic field. It's 20,000 times higher total actual field than on Earth, with a surface field 20 times larger than on Earth. And it's dominated by a plasma torus at the center. And this plasma is coming from material that is being dumped into Jupiter. It's being from the Io moon, the inner moon. It's very volcanically active and is spewing huge amounts of sulfur dioxide out from it. And that gets captured by Jupiter, and it interacts with the magnetic field, forming this plasma torus at the center. And the actual magnetopause, it's shortened on the side towards the sun because of the solar wind, but it extends all the way out to the orbit of Saturn. Now, this is just a picture of Io. I'm not going to talk about the moons, but this is the cause of all that plasma and the plasma torus, and it is also the cause of the aurora, which I'll be talking about in a second. This is now a measurement of the magnetic field that was done by Juno, and this is going pretty much from the North Pole to the South Pole, and this is wrapping around the entire planet. So you're seeing the whole thing stretched out. But what's unusual about it is how much the magnetic field varies. It just varies all over the map. Unlike on Earth, where the magnetic field has a variation, but it's much less. Jupiter has a much larger variation. And these are the polar views of the magnetic field. And I'll show you a cartoon that NASA has put together. This is a cartoon of the magnetic field, and it makes the point that the field is just all over the map. The field lines originate not just at the poles, but from various spots within even the equator region of the planet. Okay, and so the last topic essentially on this single is the aurora. So Jupiter has an aurora, but it's totally different. Its cause is totally different than on Earth. In Earth, it's the magnetic charged particles from the sun during a solar event that ionizes the upper atmosphere of the Earth, and then with the Earth's magnetic field, you have light emitted in the aurora. On Jupiter, it's totally different, and it's all due to that plasma that's ejected by the moon Io. And so it's a permanent aurora, and so it exists continuously. So the moon is ejecting these particles, and they're being ionized in the magnetic field, and they produce this light. So this is the aurora around the northern pole, and this is the aurora around the southern pole. These were taken by UV cameras on the Juno satellite. These graphs are emission of methane in both the North Pole and the South Pole. The yellow lines are actually the path of the Juno satellite as it's passing over. And you can see this is a Hubble image down here on the right. And you can see the aurora in this particular Hubble image as well. And so that's pretty much it. I was just going to show you just one picture of the moons. These are the Galilean moons, the ones that Galileo first spotted. These are the dominant largest moons. Ganymede is actually larger than Mercury, so it's bigger than one of our own planets. And not to end my talk without showing you some of my own pictures, this was one that I've sent out fairly recently this winter. This is a picture of M78, Messier 78. It's a nebula in the Orion constellation, a little bit north and west of the Belt region. But it's a true color picture, and it's the blue is a light being scattered by the stars, and the red is hydrogen emission. And this is another picture I sent out fairly recently of something called the firecracker galaxy. And so anyway, I'm going to end the talk at that point, and we'll turn it over to see if there are any questions that you folks would like to ask.
All right. So looking at, let me try and go through this here. I'm going to read a couple of questions for you, Mike, to try and answer.
Okay.
The first one was of that Hubble image that showed the Aurora at the north end, the northern pole of Jupiter. Is that I guess a real visual image that the Aurora is really that bright?
I think so. I think so. I think that is an image that the Hubble captured. So I think that's right.
Okay. Let's see. Let's see what else we got here. Are the colors on the composite images, the color images of Jupiter photo, those true colors, or are they assigned colors?
Okay. No, those are okay. A confession. They are true colors, but they are enhanced. So the colors are a little more vibrant than you could see from the Hubble image. What they, you could say that's pretty close to what they are. In my pictures, they're a little more vibrant than that. Frankly, most of the people who have done this, have made these pictures, have done the same thing. They've enhanced the colors to make things a little more apparent. But they are true colors.
Okay, great. So there's a question here asking, what is creating the gravity if it is all gas? So that goes back to your discussion about I think the gravity profiles.
Yeah, it's these the gravity profile and the wind profile, the atmospheric motion, these belts are all tied together, and so the variation in gravity is essentially occurring because of the variation in these wind patterns in the belts and zones on the planet. That was the point of those two graphs showing them at the same time. They are definitely correlated. They're related. The phenomena are connected.
Okay, there's a question about the different images of the north and south polar regions, and somebody noted that there are 8 rotating storms at the North Pole, only 5 in the south. Why would they necessarily be the same?
Well, yeah, there's no reason why there should be any specific number to begin with. But what's amazing is they say they don't change very much. Now, I say that, but I think some of the recent orbits show maybe a 6th one sneaking in on the South Pole. But okay, they're remarkably stable, and that's actually a puzzle as to why wouldn't they mix and change, and they don't seem to, at least not very fast.
Okay, there's a question about whether you could say a few words about the upcoming European Space Agency missions to visit some of the major moons of Jupiter.
I'm afraid I don't have any information on that, so I haven't looked into that, so I can't answer that question.
No problem. Another question is, can you tell us a little bit more about the resonance with Saturn? Is that a coincidence?
No, it isn't. It's not a coincidence. There's a lot of interesting resonances in once you go, like if you look at the moons, also a lot of the moons, particularly that Cassini was studying when it was going around Saturn, a lot of the moons have these resonances where it's it all has to do with the overall formation of the solar system and the interaction of all the planets. And these resonances are actually occur. Well, that's a major resonance between the two largest planets in the solar system. But these resonances occur among the moons in both Jupiter and Saturn as well.
Okay, can you talk about, you said that Jupiter was maybe close to being a failed star, but the question is, aren't the brown dwarf stars and some of the exoplanets that have been found actually a whole lot bigger than Jupiter?
They are, yeah.
Maybe it's not
Jupiter is
that
big,
close.
but there are some that are even super Jupiters. Yes, yeah.
Okay, that looks like it. I think unless I missed something, that pretty much covers the suite of chat questions that we've got. So let's see. Brent, you want to, let's see, take back over and let's see.